Okay, so I think we should start. Well, welcome to the 10th session of the GO2NE Global Ocean Oxygen Network webinar series. I'd like to welcome you all on behalf of the whole GO2NE team, and thank you for being here today. My name is Slomp, and I'm from Utrecht University, and I have the honor of moderating today's session. Before I start and introduce the speakers, I'd like to first highlight something else, and that's in fact the 53rd International Colloquium on Ocean Dynamics in Liège that will take place from the 16th to the 20th of May of this year. And this is also the third GO2NE conference, and its theme is low oxygen environments in marine and coastal waters. The deadline for abstracts has been extended to January the 31st, so you still have 5 days to submit an abstract. And if relevant, you can also apply for travel grants. So don't forget that. So it's going to be there's an option to travel there. Regarding the procedures during this webinar, please note that you have the possibility to type in questions in the question box. So please use the question box for that. The chat can be used to share additional information or if you have logistical problems. And if you want to speak at one of the upcoming webinars, please submit a short abstract, and the link can be found in the chat box. But we should start. We shouldn't waste too much time on all this intro. So we have two great scientists speaking today. First of all, we have Niels van Helmond. Then we have Laura Bristow. Both talks will be 20 minutes, followed by 10 minutes of questions and answers. And so I'm really happy to start with introducing Niels van Helmond. He's a research associate at Utrecht University. He's a paleoceanographer, biogeochemist, and his research interests are very broad. They include reconstructions of past anoxia in the ocean and studies of the drivers and consequences of modern-day anoxia. And today he'll talk about using trace metals as a bottom water redox indicator. The floor is yours, Niels.
Okay, thank you very much for this introduction, Caroline. I will start sharing my screen. Welcome everyone, and I'm seeing that I'm starting with my last slide, which is of course not ideal. No, so I will talk about trace metals today, and I've done this work with many collaborators, so they are listed here. So once again, also thanks to them for doing this great work together. Trace metals are a very nice and powerful indicator for bottom water redox conditions. And so most trace metals, such as molybdenum and uranium, behave conservatively in seawater. And so they are present in dissolved form, mostly in the form as oxyanions. But when oxygen conditions decrease in the water column, their solubility decreases and their particle reactivity increases. And this leads to sediment enrichment. So that's also nicely shown in this graph. Under oxygen conditions, nothing is happening. When the oxygen...
Niels, I cannot see your slides, so maybe you can...
Oh, that's... Okay, wait. That is very unfortunate. So, so I'll start again with this slide then. So you can see my slides now, right?
Yeah, it has to be in presenter mode still. So yeah, now it's in presenter mode. Thanks.
Right, okay. So most trace metals, such as molybdenum and uranium, behave conservatively in seawater, and they are present in dissolved form as oxyanions. But under low oxygen conditions, the solubility decreases and the particle reactivity increases, and this leads to sedimentary enrichment. And that's also nicely shown in this figure next to this. When oxygen conditions are there, there's no enrichment. In the suboxic and anoxic conditions, you see that there's some enrichment, and in the sulfidic conditions, there's a lot of enrichment. Ways of sedimentary enrichment include trace metals in organic matter, but also adsorption onto organic matter, also just diffusion from the seawater straight into the sediment, and then they can be sequestered as archegenic minerals, but they can also be shuttled, for instance, by adsorption onto iron and manganese hydroxides. And as I said, under euxinic conditions, we see particularly strong enrichments of these trace metals. Well, one of the best areas, I think, to work with trace metals is and to trace anoxia, hypoxia, is the Baltic Sea. So the Baltic Sea is one of the largest anoxic basins currently. It has a huge drainage area with a lot of agricultural land that leads to eutrophication, and in the end also hypoxia, and even worse at some spots there's euxenia, so free sulfide in the water column. And that's also very nicely shown in this cartoon by Carstensen from 2014. So in 1906, there was just very small areas with hypoxic conditions, and then gradually over the decades we see increasing area of hypoxia and even anoxia and euxenia. And here we see in 2012 that huge areas of the central Baltic Sea were actually euxenic, so that's devoid of oxygen and free sulfide in the bottom waters. So we know now that this is happening in let's say the last century, but if we go back in time, then we also see that there were other hypoxic or anoxic events. One during the Holocene thermal maximum from about 8,000 to 4,000 years ago, and one during the medieval climate anomaly from about, let's say, 1,000 years ago to 500 years ago. So yeah, there were more hypoxic events already before the modern event. And actually, trace metals can help us to learn more about these events. So we really wanted to answer the questions: can we detect differences in intensity of oxygen depletion between these different events? And can these sedimentary trace metal records help to give us new insights in the behavior of trace metals under varying bottom water redox conditions? So we set sail and we took course in the central Baltic Sea from two places. One here, the Faro Deep, and one here in the northern Gotland Basin. And we started to measure trace metals. So here's the records for the Faro Deep. And what we see here is very nicely these organic rich intervals corresponding with the hypoxic events. And we also see clear enrichments of the trace metals. So we see molybdenum is nicely enriched, and actually it scales pretty good with organic carbon. And interestingly, uranium actually is enriched more and more during these intervals, which actually maybe indicates that anoxia is increasing, so that anoxic conditions or deoxygenation is strongest in the modern event. And interestingly, rhenium, another trace metal that can be used as a redox proxy, is not showing any enrichment. So that's also interesting to note. For the second core, we actually see again a nice organic carbon enrichment, and also matched by these molybdenum enrichments. And again, uranium is increasingly enriched. So it seems to be that this is really pointing towards more anoxic conditions towards the modern hypoxic interval. And actually, really interesting to note here, rhenium is also enriched during all three the intervals. So that's the difference with the other basin. So we can do more with these trace metals. So one of the applications is, for instance, plotting molybdenum versus organic carbon, and this can say something about the hydrological restrictions. This was developed by Tom Algeo and Tim Lyons in 2006. And actually what they did is they used data from 4 different euxenic basins with euxenic bottom waters with different restriction grades. So the Saanich Inlet in Canada is actually an open system with water mass renewal about a year. And then these basins are showing more and more restrictions. So the Black Sea is, of course, one of the most restricted basins in the world, with a residence time for the waters between 1,000 and 4,000 years. Actually, that nicely plots. So the regression lines of molybdenum versus organic carbon are indeed becoming less steep. So less molybdenum can be sequestered in the Black Sea because, at some point there's not enough water anymore to renew the molybdenum inventory. So that gives you a proxy for restriction of the basin. So we can also use this proxy in the Baltic Sea. So we have separated the different intervals. So the first oldest hypoxic interval, the Holocene thermal maximum interval, and we actually see that when we plot this regression line, it's actually close to the least restricted basin, the Saanich Inlet, and it's the case for both basins. When we go to the medieval climate anomaly hypoxic interval, we see it's not so much different. So it's again around the same regression line, close to the Sonic inlet, this end number for the least restricted basin. But then very interestingly, when we plot the modern hypoxic interval, we see that this line becomes less steep. And this indeed might point towards more rapid and more widespread hypoxia. And I think I need to explain there that, okay, we know the Baltic Sea is a restricted basin, but of course, the restriction didn't all of a sudden change through this time area. So why is there then less molybdenum? Probably because the area is larger where molybdenum is sequestered, or this sequestration is going more rapid. So the hypoxia is becoming stronger, it's going faster. And that's probably why we see this regression line becoming less steep. So to conclude this part about the open Baltic Sea, we see progressively increasing uranium concentrations, which points out that the modern hypoxic interval is probably the most reducing one. We saw that there's moderate drawdown of water column molybdenum inventory during the modern hypoxic event, which suggests indeed that there's more rapid and widespread hypoxia during this time. And we also saw that molybdenum as such, just alone, is not the best indicator for redox conditions in the Baltic Sea, because this basinal restriction is having an influence on the molybdenum records. Then I would like to go to the coastal Baltic Sea, because that's also an area where we can use trace metals. So we know that the coastal areas of the Baltic Sea are also deoxygenated. This is a very nice compilation of data by Conley et al. In Environmental Science and Technology. And we actually indeed see that all these black dots are areas where we have found eugenic conditions over the past decade. And they are mostly centered here in the Danish Straits, and here in the Stockholm archipelago and in the Finnish archipelago. And actually, I want to zoom in today on the Stockholm archipelago. So our main questions are, was the Stockholm archipelago hypoxic prior to the 20th century? Yeah, so we know in modern time it's hypoxic, but was there already hypoxia or worse before that? And when was it hypoxic? Can we, for instance, recognize similar intervals as we saw in the deep basin? And then, ideally, we would also like to answer the question whether humans were involved in this. Was there, for instance, already an influence from human settlements? We know the Viking era, of course, huge areas were made agriable. So could that be an influence for hypoxia in the past as well? So we samples, of course, in three different basins in the Stockholm archipelago. In the Barnensfjärden, the most restricted one, where we know today we find seasonally hypoxic conditions, even sometimes euxenia, and two sides to a bit more to the open Baltic Sea, where we have a different hypoxic condition. So in the Estevieke side we have hypoxic conditions, and in the Ingarofjärden it's generally oxic. So we have some contrasting redox conditions there. So here we first look at human or anthropogenic indicators, and actually two very, very good indicators for that are the trace metals lead and zinc. And so we see very nicely here a pattern appearing with the onset of lead pollution around 3 meters in the deepest core, and somewhat shallower in the other cores. And then actually we also see the start of zinc enrichment, and we see a maximum in lead pollution, and that's correlated to the use of unleaded fuel from the 70s onwards. So then we know a little bit where we are in time, so we know a little bit about the timing, but then of course we need to still know the redox conditions. And for that we have measured here organic carbon and molybdenum. So what we actually see is that from the base of the deepest records, we see there's high organic carbon and also relatively high molybdenum. So I've kind of shaded areas where we think conditions were hypoxic or worse. We see there's at least one hypoxic period before modern time appearing. So of course, then we want to know exactly when this was. So we have constructed the age model, which can be found in this publication, based on radiocarbon dating and lead-to-tin dating for the top sediments. And actually, what we see then is that we have these hypoxic conditions starting, or at least starting, 1,000 years before Christ, so about 3,000 years ago, and that actually continues to about 1,400 years AD, so 600 years ago. And then actually we see a period where the hypoxic conditions decrease. So actually molybdenum almost goes back to background and only increases again here in modern time. And actually when we then connect again to this human influence, the trace metals that are indicating anthropogenic pollution, then we see actually that there's not really a clear evidence that hypoxia is linked to human influence. Actually, it's the other way around. So we see human influence is increasing from 800 AD onwards, and actually hypoxia is decreasing during that time. And only in the last century, we really see that there is hypoxia again that we can directly couple to human influence. But what is causing hypoxia then in this coastal zone? Well, we have also constructed a temperature record based on a biomarker proxy called X86. And actually what we see is that it was much warmer, or it was warm, relatively warm before this non-hypoxic period. And actually the period where we don't find hypoxia is also known as the Little Ice Age in northwestern Europe. So we really see that there's a coupling between temperature and deoxygenation of the water column in the coastal zone of the Baltic Sea, or at least here in this part of the Baltic Sea, the Stockholm archipelago. So to conclude, there are two periods of hypoxia recognized, at least two periods, I should say. One prior to the Little Ice Age, so we know it goes back to at least 1,000 years before Christ, so 3,000 years ago, and one since the 20th century, which we know is the modern hypoxic period. We don't see evidence for the coupling between human activities and hypoxia before this time. And I think we can clearly show that temperature is very important in determining the redox state of the bottom waters in the coastal Baltic Sea, which is of course also the case on a global scale. Then I want to touch shortly upon a last interesting application of trace metals. So we've been studying this coastal marine lake in the Netherlands. It's called the Lake Gevelingen, and actually in one of the deeper pits, we've been doing all kinds of studies. And actually, very nicely, what we see there is these seasonal molybdenum spikes, and that's actually very nicely showing the deoxygenation in this basin, which is seasonally indeed hypoxic or even euthynic. And we really see these peaks appearing on a yearly basis. So really, this is the summertime of 2014, for instance. But actually, there's another application to that, because when we were putting these sedimentary molybdenum enrichments, they actually very nicely correlate with the area of the lake that has oxygen below 1 milligram per liter. So there's actually a very strong correlation. This might be coincidental, but yeah, this shows maybe that there's more applications to this molybdenum trace metal proxy. And actually, some very recent research, we've been sampling in Lake Gevelingen on a seasonal cycle last year. And actually, in March, we indeed find a molybdenum peak from the last summer. And actually, during the season, so we did sampling trips every month. During the season, we see actually the growth of a new molybdenum peak. So here we see the summer of 2020, and here we see this molybdenum peak in the summer of 2021. And actually, that's for us also a great tool to date sediment. So now we know this is the summer of 2020 and this is summer of 2021. So we can really derive also a sedimentation rate even from that, which is 20 centimeters in this case, which is very useful because in these kind of settings, you cannot use lead-210 dating. So yeah, that's another really nice application of trace metals. Okay, then I get to my last slides. I think I've shown that sedimentary trace metals are very powerful indicators for bottom water redox conditions. That was, of course, also my title, but I think there are many more purposes, such as tracing human pollution, reconstructing hypoxic lake area, and sediment dating. With that, I would like to thank the organizers for this very nice webinar series, and I would like to thank you for your attention.
Okay, thank you very much, Niels. We have plenty of time for questions. You're very nicely within time. So if there are any questions, please put them in the chat. I don't see any at the moment, so I will put a question forward first. That's actually, you haven't really spoken about, let's say, for those 3 events, the drivers. So what's really your conclusion about the drivers of hypoxia during these 3 events in the Baltic Sea?
Yeah, so you're referring to the open Baltic Sea here?
Yes, I'm referring to the open Baltic Sea.
Yeah, yeah, in the past, so I need to go back to one of my first slides. In the past, we also know that there are actually climate variations. We do see that indeed during these other hypoxic events, so during the medieval time and also during the Holocene thermal maximum, that there were actually warmer climate intervals. So yeah, during the Holocene thermal maximum, there are some reconstructions that global temperature was up to 1 or 1.5 degrees warmer, and during the medieval climate anomaly, this might even be more in northwestern Europe. And another reason for the hypoxia to occur is obviously the restricted basin configuration of the Baltic Sea. So there's a strong halocline, so which makes this the water column very stratified. Yeah, so that explains actually why this basin is hypoxia prone in the first place. Yeah, and for the modern interval, we know it's of course our human footprint, probably in combination with the climate as well, warming. Yeah, so those are the main factors.
Okay, I see some questions now coming in. So there's a question from Andreas Oschlies. Can the isotopes be used to record the volume or the sediment contact area of any local anoxic water pockets? Or do they even record volume or sediment contact area of the entire Baltic?
Isotopes can definitely be used for that. So isotope systems of molybdenum and uranium, but also other trace metals are used to determine at least areas. And I think, yeah, in theory, depends how good your knowledge is about basins. And yeah, I guess you have to make some assumptions, but I think in the end you can get to a volume as well. But I think that requires quite some assumptions. So I think for relatively recent reconstructions, it can be done. But if you go, the further back you go in time, I guess the more difficult it gets. But that's logical. But yeah, I guess it's difficult to use just what I showed here is mostly just concentrations. Yeah, I would ideally you combine, of course, both. And when you measure isotopes, I assume you also know the concentration. So yeah, then I would say you can get quite far.
Okay, there are quite a lot of questions, so let's see if we can get them all answered here. So do you think that this would also work in shallow tropical marine sediments? This is a question from Rachel Collin.
Yes, I wouldn't see a reason why this wouldn't work. I guess the kinetics and the process behind trace metal sequestration are the same in every setting. So I would definitely expect it to work in those settings as well.
Okay, and so then there's another one. David Kirchman is asking, why is molybdenum such a good indicator of hypoxia? And then there's a second question related to it. What's the mechanism explaining the high correlation between molybdenum and organic carbon?
That's a nice one indeed. Yeah, so molybdenum is very well known that it's actually sequestered in something that's called the sulfide switch. So molybdenum is naturally occurring as molybdate, so the oxygen ion, and then when there's sulfide present, it forms thiomolybdates, and those are insoluble. So that's from about 12 micromolars. 12 micromolars of sulfide. So then molybdenum is kind of taken from the water column. So that makes yeah, that makes it a really really strong really strong indicator for hypoxia, or actually I should say euxemia, because it's sulfide. But usually, yeah, this can happen of course also in the sediment. It doesn't really necessarily have to happen in the water column. Yeah, so the organic carbon relation is there because also a lot of molybdenum is absorbed in the end onto organic carbon. So in that case, it's really associated with the organic material. So that's when it really is in the sediment. Yeah, it's there. Therefore, that's the strong correlation there. So it's not really part of the organic material, because then, yeah, I mean, it's usually really the content of phytoplankton and molybdenum is really low. So it's really a diagenetic process that makes it yeah, correlating with organic matter. Yeah, so I hope that kind of answers the question.
Yeah, so there's another one related to the organic carbon. That is, did you determine the origin of the organic carbon? Is it continental origin or marine? This is
yeah, no, that's also a very nice question. So actually, we did that for the coastal Baltic Sea, because I was actually expecting to find a lot of organic matter derived from land. So yeah, you see, we find typically 6, maybe yeah, in the not so hypoxic periods, or not the oxic periods, it's still a 3 or so. So that's quite high organic carbon content. And actually, the biomarkers that we use to derive temperature from also say something about the organic carbon origin, because part of these biomarkers are actually produced by microbes that live in soils. So this is called the BIT index. This was a proxy developed in the 2000s by the Niels group, the Royal Dutch Sea Research Center. And actually, I also calculated that, and actually we also have shown that in our paper. And actually, even for this coastal zone, we saw that most of these biomarkers are actually marine derived, which I was really surprised with. But I think in the end, it's not that strange, because a lot of nutrients are brought into the system, and you have huge algal blooms. And so apparently in the end, a lot of the organic matter is still of a marine source. And actually, also another way to look at it, which shows a similar picture, is looking just simply at the molar CN ratios. And those are actually also very close to the marine end number. Yeah, so that's actually very surprising. Yeah.
Okay. We have a lot of questions still to go, Niels, and little time. So there's a question from Christopher Bouya. Did you identify more precisely the processes that drive accumulation of molybdenum and uranium and their difference during anoxic phases? Is there a secondary accumulation in the sediment itself? How does it influence the record?
Yeah, that's of course a very good question, and actually I can be pretty short on that we didn't really look into that. We did look into detail about phasing between molybdenum and uranium enrichments for these deep Baltic Sea cores. So because of time, I didn't show those data, but we did look at with in high resolution with laser ablation ICP-MS. And we do see that uranium is actually always leading molybdenum more or less, which is actually not a surprise, because we know that uranium is already being sequestered in the zone of iron reduction, and molybdenum is really connected to the sulfide switch. But yeah, in detail, looking in what phases and so on, that would indeed require specific microscopic techniques, and we didn't apply those. But that would be definitely something to still do in the future.
Okay. Then a question from Mark Wells for the coastal cores. Yeah, again about marine and terrestrial processes, but there's a specific question there. Have you looked at the abundance of cyanobacteria to look at planktonic processes? Or comparing your cores to those?
Yeah, no, so actually that is also, again, a good question. So we have been talking about it, and I guess we may have some preliminary data on that, but I have to say that we didn't really do that then. No, because
Okay, then one
Yeah.
final question that is from Terence Long on our NATO SBS program in the Baltic and North Seas. We found that around most decaying munitions, TNTs, anoxic zones, same concern in other seas. Have you considered munition as a potential source?
No, we actually didn't. No. Yeah, I can be short on that. Yeah. Yeah, I'm aware of those data sets, but we didn't really think of that in this. I know that, for instance, areas around the Bornholm Basin are indeed used as a munition dump site. Yeah, so we didn't, and there's also actually a dump site in the area where we have sampled, but not the exact area. But yeah, so that is something that could play a role. Yeah.
Okay, thank you. We need to stop here because
we have
to leave enough time. So thank you, Niels. And then the people that, the questions that have not been answered, Niels will follow up to answer those questions. So thank you, Niels. Then I'm very happy to introduce our next speaker, Laura Bristow. Laura is an associate professor at the University of Southern Denmark. She's a microbial ecologist and biogeochemist. She's specifically interested in nutrient cycling and oxygen minimum zones. She, in fact, has just returned from a cruise. So it's incredibly impressive that she is here today to give this presentation. And she will be talking about nitrogen cycling and anoxic zones. So the floor is yours, Laura.
Thanks so much. And it's great to see so many people here. And okay, does that look good to everyone? No, let me start the slideshow. Does that look good?
Yes, looks good.
Excellent. Okay, so yeah, thank you for everyone who's here today, and thank you to Caroline, and thank you to Niels for a great talk and getting this started today. So yeah, I really want to talk to you today about nitrogen cycling in anoxic waters and some of the challenges associated with that, and the ideas that we have about kind of maybe it's time that we need to take these measurements in situ. I probably don't need to explain this to a huge amount of you in the audience today, but just let's kind of take a look at some of those low oxygen regions that are familiar to us. And so here's kind of the global ocean and looking at the oxygen distribution at 300 meters depth. And it's those cold colors, those purples and blues, that are those oxygen minimum zones that we're familiar with in the Eastern Tropical Pacific, where I've just come back from, and also over in the Arabian Sea. And these regions they're naturally occurring phenomenons, and that's because these are regions of upwelling. And so we have upwelling of nutrient-rich waters, kind of stimulating productivity, and then subsequently kind of the rain down of organic matter. And as that's respired, that consumes the available oxygen. And also these are regions that are relatively sluggish ventilation-wise, resulting in these low oxygen regions. So I call them oxygen minimum zones. Other people call them oxygen depleted zones. Some people call them anoxic marine zones. But what does this really all mean? And what oxygen concentrations are we actually really talking about? And so here we've got a nice section from the just off the coast of Mexico, kind of using a stock sensor. So a switchable trace oxygen sensor. And this kind of starts to give us a feel for kind of what oxygen concentrations we're talking about. And regularly, it's kind of below the limit of the detection of this stock sensor, the best technology that we have available. And that detection limit is somewhere kind of a few nanomolar within that core kind of region of low oxygen. And it's those kind of numbers that I want you to keep in mind as we move through this talk. And so we're running out of oxygen, or it's completely gone. So how are we going to continue to respire organic matter? And so that's where nitrate comes in, and hence why I want to talk about the nitrogen cycle today. So nitrate is the next preferred electron acceptor for respiration after oxygen. And as you can see here, if we look at this from kind of an energy standpoint, there's actually not that much difference between the two. And so when we use nitrate, we talk about the process of denitrification, where nitrate is reduced sequentially to N2, and that N2 is actually lost from the system. And so oxygen minimum zones are actually responsible for 1/3 of marine nitrogen loss, even though they actually only make up about 0.1% of global ocean volume. And so let's take kind of jump in a little bit more to the nitrogen cycle. And this is, I'm sorry, it's still kind of complex, but actually a simplified version of the nitrogen cycle for those that are more familiar with it. And the reason I really like this version of the nitrogen cycle is because it we've got anoxic at the bottom and oxic at the top, really suggesting that we might kind of have a real clear line or a clear cutoff between when we switch from aerobic to anaerobic processes. So you'll see in the bottom half, those anaerobic processes, so that denitrification, the gray arrows that I spoke about, process I spoke about already, denitrification. And we can also have the process of anox, and those two, denitrification and anox, are both kind of producing N2, which is then lost from the system. If we look at the aerobic processes in the top half, particularly nitrification, that's when ammonia is oxidized to nitrite and subsequently to nitrate. But then maybe we would expect that we wouldn't see these aerobic processes within these low oxygen waters, and we would only see denitrification and anox. But if we actually sort of start to dig into the literature, we actually are regularly seeing occurrences of aerobic processes. And so here's some nice work from kind of Tim Calvalaga, and here we are off the coast of Peru. And these are kind of depth integrated rates. And so looking over that whole kind of chunk of low oxygen water, and kind of I've tried to mark on what processes we would typically think of as aerobic and so require oxygen to occur versus the anaerobic ones. And so we've got the anaerobic processes here. We've got kind of nitrate reduction to nitrite, which is the first step of denitrification up there in the top right. And here along the bottom, we've got the complete process of denitrification and anox. We can see, maybe as we would typically expect them to be occurring in the low oxygen waters of Peru. But maybe more surprisingly, we've got these two steps of nitrification occurring. So both thought to be aerobic processes, oxygen requiring, and they both are kind of, they're going along. And even at speed, if we look at some of these numbers, they're kind of happening at a similar magnitude to some of these anaerobic processes. And this has kind of really spurred us on as a community to really kind of ask ourselves the question, what extent do these processes, so those aerobic and anaerobic processes, co-occur, either supplying or competing for substrates involved in nitrogen loss, therefore maybe controlling how much nitrogen loss is occurring within these systems. And therefore, we've really been working to kind of assess the oxygen sensitivity of these processes, and most importantly, down to oxygen concentrations present within the core of the oxygen minimum zone. And so down at those few nanomolars that we were looking at a few slides ago. And so kind of just to quickly go back to the nitrogen cycle image here, I mainly am going to have a look at the oxygen sensitivity of kind of denitrification anox, and so those nitrogen loss processes. And then we'll have a look at the oxygen sensitivity of nitrite oxidation and really think of that as a recycling process, because that's kind of really then just, it's still kind of keeping nitrogen within the system. And so, yeah, those nitrogen loss processes first. And so in the graphs on the top here, we've kind of got oxygen concentration on the x-axis, and then the y-axis is inhibition. And by this, I mean that when there's 100% inhibition, that means we can't detect the process anymore. And so it's not occurring. And so you can really see how sensitive these processes are to relatively small amounts of oxygen. And so how I'm going to kind of then refer to this, just to help us put some numbers on it, is I'm going to use the term 50% inhibition. And so therefore that is the oxygen concentration at which 50% inhibition of the maximal rate was obtained. And so if we look at the first step of denitrification, quite a lot of different kind of groups and I have looked into this in different kind of low oxygen waters, and there the 50% inhibition covers a huge range. We're seeing a really strong discrepancy between studies, and with them ranging from, below a micromolar all the way up to more than 20 micromolar of oxygen. And I can't really get into that with the time available today, but I would be happy to talk about it with people thinking about whether that's driven by particles, different microbial communities, etc. And so then if we look at kind of that 50% inhibition value for denitrification anox, we're looking at values of about 200 nanomolar for denitrification and about 900 nanomolar of oxygen for anomox. And so then how does this then compare if we then look at one of those aerobic processes? And so here I want to look at nitrite oxidation. And so this is nitrite being oxidized to nitrate. So again, this is us more recycling nitrogen in the system because we are not losing it like we were in the processes on the previous slide. Here a slightly different plot, oxygen still on the x-axis, and then on the y-axis is just the rate of the process. And here it very nicely fits Michaelis-Menten fitting. And then what I've done is I've calculated a Km value, so a half saturation. And so again, thinking about how much oxygen for about 50% of the maximal rate. If we just look at kind of the black line, the black fit, that's kind of a single component Michaelis-Menten. We get about 800 nanomolar of oxygen. Actually, we get a much better fit looking at two component, the blue one, especially at the low end, which you can kind of see in the inset here. And there with the two components, we actually have one component that would have a Km value of less than 1 nanomole. And this is exceptionally low, suggesting we have maybe a part of the community that is really kind of able to take advantage of any small amounts of oxygen available. But all in all, it really, even though we know this is an aerobic process, it really has a strong dependence on nanomolar concentrations of oxygen. And while this process is strongly suppressed under kind of these very low nanomolar conditions, we've never actually been able to switch it off completely. And that's kind of why some of you may have seen the literature sort of talks about the potential for maybe anaerobic nitrite oxidation occurring. And there are many kind of, speculations right now about what that mechanism might be. And I think one of the questions is what the extent of that process would be, which I think we'll come back to over the next slides. So I hope I've kind of made you see that really all aerobic and anaerobic processes in these low oxygen waters are highly sensitive to nanomolar concentration of oxygen. But kind of us hanging out in the lab or on a ship, how kind of are we able to assess the extent and interactions of these processes with current sampling and experimental techniques? Because we've got water down kind of 100 meters of depth that has, undetectable levels of oxygen in it. How can we then get it up into the deck or into the lab and carry out incubations at maybe oxygen concentrations similar to those in situ? And for a long time, a lot of people have made the assumption that oxygen concentration during incubations have been assumed to be equal to in situ levels, but the concentrations have actually been rarely measured. And so now I kind of really want to kind of take you through and us have a little think about together, what could be kind of the impacts of putting this low oxygen water into a Niskin bottle, how we're going to bring it up onto the deck. And how kind of just an experimental procedure like the one I've shown here, kind of how I would carry out an incubation experiment, is this actually getting me to conditions that would be similar to those in situ? So let's take a look at sampling first. And so here I'm mainly going to talk about putting it inside a Niskin bottle. And so I think we've all, maybe those of us who go out to oxygen minimum zone sampling, have suspected this for a long time, but Emilio Garcia Robledo has just published a fantastic paper in LNO last year that's really kind of put some numbers on what oxygen contamination during sampling would be. And so here, this is us thinking that we've sent a rosette down with these Niskin bottles, and then we've closed them within the kind of the water that we know to be below the detection limit of our best technology. But then by the time that we actually get that Niskin bottle back onto the deck, it can actually, Emilio managed to measure up to oxygen concentrations of up to 1 micromolar within the Niskin bottle. And this is simply due to leakage from the Niskin bottle material. He also very nicely showed that subsequent sampling can even potentially increase this oxygen contamination even further. And you can kind of see that in this figure that I've taken from his paper here. And so here again, this is the Niskin bottles being closed in those anoxic waters of this is in the Eastern Tropical North Pacific oxygen minimum zone. Then this is him trying to sample And then the white bar is just kind of then trying to fill a glass bottle, and this is just letting it overflow multiple times. And you can see then he's measuring concentrations more than 1 micromolar in that bottle. And then when he's submerged the bottle, and so then it's being kind of as the water overflows, it's then that water is then eventually submerging the whole bottle. He's still kind of showing concentrations in kind of hundreds of nanomolar. And so clearly this demonstrates that if we want to sample these waters and then carry out incubations, we are going to need to kind of carry out some kind of deoxygenation. So some kind of oxygen stripping after sampling if we are going to try and return to in situ conditions. Unfortunately, it would be really nice if then we could just say, you know, bubble our samples of helium for a long time and get down to very low levels. But unfortunately, there are a few other things that stand in our way. And so one very typical thing for us to do as a community is to then put the water into a glass vial of some description and then bubble it with helium. And then we would cap it with some kind of rubber stopper. And then there's some examples in some pictures here. But unfortunately, oxygen is easily soluble in and also diffuses through plastic and rubber components of experimental setups. And here in this image in the bottom right is an example of what can happen, that you can have very low oxygen concentrations at the start of your incubation. And so here, this is a glass vial with one of these blue caps on that's then got a thin butyl septor on. And then what's happened is it's just been left. And you can see that from that cap over just 4 hours, micromolar of oxygen have come in to the experiment. We as a community have worked hard to try and think about ways to get around this, you know, using less plastic and rubber wherever possible to try and avoid this. But unfortunately, it's hard to avoid it completely. And so then with things like these rubber stoppers that I show you, it's now very common for us to keep them under helium for months before we use them to try and deoxygenate them. But still, even though we're carrying out these extensive procedures, it still is very difficult for us to get to in situ concentrations. And we're still showing in these incubations that there can be sometimes tens of nanomolar or even more oxygen still present. But something we do urgently need is more studies to carry out oxygen measurements within incubations that they do. And this is not just for nitrogen cycling, this is kind of for all experimental work that is done in these low oxygen waters. And so myself and a number of other people, my great collaborators listed at the bottom of this slide, have kind of been thinking for a number of years or even longer, especially Bo, thinking about kind of producing some kind of in situ incubation system. And here we have kind of been working hard on this system that you can see in these pictures of trying to come up with an oxygen contamination free in situ sampling and incubation system. And so this, it all happens, we deploy it to our depth of interest. So within those anoxic waters, and all the sampling and the incubation happens at depth. So this used to be we basically adapted a system that used to be for productivity measurements in seawater. And then what we've it's a glass chamber, which you can see in the middle image here. And just think of it almost as like a big glass syringe. And it just has then a piston, and then it allows us to flush the chamber well before then we fill and the tracer is injected. And then basically we can push out at program time points, allowing us to get nice time series for our rate measurements. We've then replaced all the plastic and rubber with titanium, which you can see in the images here. And the other thing that we've added is to kind of be able to monitor oxygen. And that's that big titanium cylinder that you see in a lot of the images. And so this enables us to both monitor oxygen within the chamber during the whole incubation and also outside of the chamber, with obviously our big hope that those numbers will be almost identical. And so I can tell you they certainly weren't at first, and it has been a long road, but I can very kind of happily show you some examples of some work we've done recently. And so here in the kind of the top panel is kind of then oxygen concentrations on the y-axis, and X is time. And in the top one, this is the oxygen concentration we're measuring outside the chamber. And so initially you can see it's dropping quite quickly. And so this is the unit kind of coming to its depth where it's then going to sit for the incubation. And oxygen concentrations actually drop below the detection limit of our sensors, which is about 1 nanomolar here. And so, okay, we're in water with less than 1 nanomolar oxygen. So then how do things look inside the chamber? And so that's the bottom panel. So we actually deploy the system with sodium dithionite in it. This is then allows us to have a chemical zero for our optode sensors, allowing us to basically get a 0 measurement of oxygen in situ. And then the idea is the chamber is flushed a number of times, and that allows us to flush out all of that dithionite. And then at this point, then the chamber is filled. And then that's when the tracer is injected. And then we take a sample pretty much immediately. And that goes into a kind of a foil bag, and it's got preservative in it. And then the incubation kind of continues on. And then we can take subsequent samples later on during the sampling. And as you can see, and very happily can say that inside the chamber is also kind of below the detection limit. And so we really seem to be able to carry out an incubation without any oxygen contamination, and hence at in situ conditions. We headed out into the central Baltic, so I very much agree with Niels here that it's a great sampling site. We headed out in August of last year. And here is just some profiles. So this is kind of standard practice. And so you can see that oxygen kind of disappears, and it's gone by about 71 meters. And then here, very much as maybe we would expect, then we see nitrate disappear, those green squares. We even see sulfide start to accumulate those open circles. Then at these depths, we took samples for standard kind of lab incubations. And that's what I've got here. These are not from the incubator. We'll get to that in a minute, don't you worry. But these are from excitator experiments. And so here we've kind of looked at, we added labeled nitrate and then kind of followed it around. And so first of all, you've got nitrate reduction rates. And so that first step of denitrification, nitrate going to nitrite, you can see that rates reach pretty high of about 1500 nanomolar of N per day. And then we also looked at N2 production rates, and they reached up to about 50 nanomolar, which is relatively in agreement with some work done by Tade Ausgaard in the region a few years back. And we measured oxygen concentrations in a subset of these excitators, and they were always less than 30 nanomolar, but we could still always detect oxygen. So we deployed our incubator at 73 meters depth, and these are the numbers that we have. And so you can see if then the nitrate reduction rate that we measured at the incubator depth, as you can see, it's significantly higher than those we measured in the lab. And the same can be said for the N2 production. And here I've just kind of shown you the nice time series. And the same goes for nitrate reduction. We have a time series for that as well. And the same goes for N2 production. We're seeing a significantly higher rate than we were in the lab incubations. Unfortunately, this is still a work in progress. And so we weren't able to do a whole host of deployments, but we did do one more. And there we did a second incubator deployment. And this one, unfortunately, there was an oxygen intrusion came through just after we deployed the instrument. So we thought we'd deployed an anoxic depth, but there was actually a couple of micromolar oxygen. And because of this reason, we actually don't have a perfect lab comparison for me to show you. And so that's why I've just kind of put some numbers up on the screen for this one. But we were, even though there was 2 micromolar of oxygen present within the incubator, still able to measure both rates of nitrate reduction and N2 production. And so just to bring this all together and give you an outlook for where we are headed, I believe, I might be wrong, that these are some of the first in situ measurements of nitrate reduction and N2 production in low oxygen waters. And we are really seeing a large difference relative to lab-based rates, but I don't think we all need to rush away just yet and think that everything in the literature is an underestimate. We certainly need to do more measurements with this incubator. And so, yeah, watch this space, definitely. But in situ incubations are certainly going to be critical for us to understand the extent and interactions of biogeochemical processes for the nitrogen cycle and beyond. But I should really emphasize that this can really not replace lab measurements completely. We have too many questions about substrate availability, for an example, for us to be able to do all of this in situ. But I really hope that will allow us to put our lab experiments more into context. But something that we do urgently need to do is we need to do more oxygen measurements within our lab incubations to really have a good feeling for what oxygen concentrations we are actually measuring our rates at. And I really hope that we are all moving towards then a new era for kind of process studies. And finally, I want to thank all of you for being here today. And I certainly couldn't have done it without both Amdrup, Morten Larsen, and Sarah, Jaime, and Anis here at Nordsee with me. And a big shout out to Ginny and Maria at Woods Hole, who this also certainly would have been possible about, and Volker, who made our sampling in the Baltic possible this year. And yeah, I'd love to take any questions or hear any comments that anybody has.
Hey, Laura, thanks. This was a great talk. We don't have a lot of time for questions, so we should start with them quickly. A question from Mauricio Urbino: why helium instead of just N2?
Oh, yeah, that's a great question. And so it's mainly because we are interested in looking at N2 production. And so if I then flush with N2, my N2 background will be huge. But if you were interested in a process that wasn't N2 production, nitrogen would do just as good a job.
Okay, then there's another one from Darcy Rush. She calls us excellent work, very exciting. And when will the in situ samplers be put into mass production? Oh no, wait a minute, that's not a serious question, I think. But are all these incubations happening at depth, or do you bring them up?
It's happening at depth. And so, yeah, it's kind of us deploying, whether it's on a mooring or floating array of some description. But yeah, so it's happening at depth, allowing us to then really also have the in situ temperature and pressure aspects also taken into consideration.
Okay, so yeah, it means you cannot do a lot of sampling. I mean, you can only do very few depths.
Exactly. And so, yes. And so certainly, yes, we would need several. And at the moment, we just have one chamber. But then we're really, we've been working hard to find the best. But our hope is then would be to kind of have a number of chambers at least lined up next to each other. So we could do, say, different types of incubations at the same time.
Yeah, there's another one, Terence Long, again about munition. It's asking if the munition is a major source of ocean nitrate and source of deadly green and blue algal blooms. Do you think munition plays a role in the nitrogen cycle in the Baltic Sea?
I'm not sure I have a good answer to that. I think that's a good question, but I'm not sure I have an answer. I'm sorry.
Okay, next one, Gonzalo Gomez has a question. He also says it's an excellent talk. How much volume of water can you get with your super fancy new in situ devices? Have you checked if there are substantial changes also in microbial community activity?
And so, yeah, that's a great question. So at the moment, our chamber is 400 mil. And so therefore we push out about 50 mil at a time, just because we don't want the total volume to be too small for the final time point. Great question about the community. Yes, that is a work in progress. And so the idea would be is that then we actually would have another device next to it. And there we would actually take samples for the microbial community at the beginning and the end. And so to see whether we did see any differences, but you're right, it's certainly something that we do need to check.
It's also a question from Andy Dale. Any idea of what fraction of pelagic N loss takes place in submicromole oxygen waters in the OMCs?
That's a big question. I think I'm not sure I could give you a good number for that, but I think it certainly is us doing more. I think we do a lot of incubations at then trying to go for anoxia, but I think it is certainly trying to think about doing it at kind of between kind of that few hundred nanomolar range is certainly going to be certainly worthwhile. And I think the extent of those waters is also something we don't understand, particularly with oxygen intrusions. But I think it's a great question and something we need to work on more for sure.
Okay, and there's another question, Ivan Koneza, I hope I pronounced the name right. Alcolea has a question, next step also to look at carbon nitrogen ratios for biochemical actual processes and model them to adjust.
No, yeah, I think you're right that we certainly need to look at the carbon side of things as well. And so then we can start to produce kind of, yeah, ratios like that and think along those lines. And so I know that, for instance, Maria Pakiadaki, who's working with us on this, is very interested in doing dark carbon fixation rates in the same kind of setup. And so then we really can start, yeah, to get questions like that. And yeah, maybe one day we'll be ready to adjust things, but I think we might be a little way from that, but I certainly feel we're heading in the right direction.
Okay, good. I think we have most of the questions now, and I skipped a lot of the compliments there, so just I can say those here and now at the end. A lot of people saying that this was a great talk, excellent talk, very interesting. So very, yeah, great work. So yeah, with that, it's also 5 o'clock, so we have to end. And so I really want to thank both Niels and Laura for great talks. I want to thank the audience for the active participation. We had a wonderful discussion, I think. And we're looking forward to seeing you again at the next webinar, and it will be in February. The exact date and topic will be announced. So I wish you all a nice day, and thanks a lot for being here. So it was great to have this meeting today. Thank you.